Yeah, so by the way, I talked to a few of you about the progress of the team projects. So I think it would be nice if you can start to just reach out to your teammates, okay? Because you want to do that early, right? Even if you're not dealing with the actual contents of the project, I think it's always good to know who your team members are. So when time gets started, right, to work on the projects, you can just reach out to them. I would suggest that you can create some like WhatsApp group or some other groups, right? Or through the Canvas. I think on Canvas, you can have all the contact information of the classmates, right? So you can try to identify who your team members are and then reach out to them. Right? It's always good to start early and get prepared, okay? Okay, so it's already 10 and let's get started, all right? So this class, we're going to finish the discussion on the cyclones. So it's more about the mathematical design and calculation of the cyclone systems. So before that, let's do a quick recap of our last class, right? So last class, we mainly talk about the mechanisms of cyclones, right? So basically, it's just using the spinning or the rotational speed or the rotation of the airflow so that we can remove these particles, right? So we know that in order to maintain the rotation of the particles, we have to provide a centrifugal force, right? So in the cyclones, it is actually the drag force that's acting as the centrifugal force. And we know that the centrifugal force is calculated by mb squared divided by r, right? So which means that the larger the particle, the larger the centrifugal force it requires to make those rotational movement. So that's why for the larger particles, they don't have a large drag force to support this centrifugal force, right? So that's why they get spinned out, let's say, just onto the wall, right? And then get collected. So in the cyclones, it works in a way that we just inject these airflow from the side of the cyclone, and then it has to make this spinning movement. And then basically after the larger particles are being removed, or it's kind of like a washing machine, right? After they're being washed, right? So the cleaner airflow is going to exit from the top. So here I'm also showing you this schematic diagram of the cyclone. So you can see that there are a lot of, I would say, dimension parameters or design parameters. As we mentioned, there are, let's say for the inlet, you have the height of the inlet, the width of the inlet, right? And then for the body, you have the body diameter, right? And the length of this cylindrical part, right? And the length of this conical part. And you also have, let's say, the exit, the diameter of the exit, and the diameter at the bottom for the collector. And then we show that for the cyclones, there are basically two equations that we are generally going to use to calculate its efficiency. So first is the cutoff size, right? And it indeed looks quite complicated, but we show that at the end of our last class is that we can quite easily derive it just by using the concept of the centrifugal force and the drag force, right? So what we did was we just equate this thing with a drag force, 3 pi mu dp divided by multiplied by VR, right? VR is a relative movement between the particle and the airflow. And we can actually solve what is the cutoff size, right? So basically the cutoff size is kind of the characteristic size of any cyclone, of any sizes, right? And later we'll show that with this cutoff size, we can calculate what is the efficiency at on any other different sizes. So we basically show that when, let's say, dpj is equal to dpc, we found that eta is equal to 50%, okay, which means that at the cutoff size, the removal efficiency of the particle is 50%. And then when dpj goes to, let's say, goes to 0, right? When the particle size goes to 0, which means that particles are becoming very small, eta goes to 0%, right? So the cyclone is very ineffective to remove smaller particles. And when dpj goes to infinity, we have eta goes to 1, goes to 100%, okay? So the reason is that, right, you see when dpj goes to infinity, then this term here goes to 0, right? 1 plus 0, that's 1, and 1 divided by 1, that's 1, right? 100%. So basically, this is the equation that can allow us to calculate the efficiency at any different size. Right? And then it becomes pretty clear that if we were provided with a cyclone, let's say, if the, let's say a design company give us all the dimension of the cyclone, theoretically, we can predict what is the efficiency at any different sizes, okay? But the thing is that in a lot of the industrial applications, what we are provided is not single size. It is the size distribution, right? And most of the time, there are log normal size distributions. So how do we calculate the efficiency or the overall efficiency of the cyclone for this wide spectrum of size distributions, right? So we're going to show that later on. But before that, we have to address a question, because you see that for the cyclones, there are just so many design parameters, right? So how do we find one? How do we decide what diameter, what kinds of dimensions we should use? So luckily, there are a lot of engineering experiments that actually help us to identify a few combinations of these designs. So basically, we can divide the cyclones to 3 different types. Okay, so this is talking about the type of the cyclone, and we can divide them into the high efficiency one, the conventional one, and the high throughput one. Okay, so for example, if we just try to focus on the conventional type of the cyclone, and then we're interested in number 3. Okay, so we're going to choose this set of parameters here. So you can see that while we have these values, but on the left-hand side, these are just the ratio between all the dimensions over the body diameter. Okay, so this is H over D, right? And this is W over D, the DE over D. So everything is basically taking a ratio over the body diameter. So now, for example, if we decide that the body diameter is 2 meters, okay, so how do we calculate the H and W, right, on all the other dimensions? We just need to look into this table here. And then first we see that in terms of the height of the inlet, the H over D is equal to 0.5, right? So that means that H over D is equal to 0.5, right? And we have D is equal to 2 meters. So H is equal to 1 meter, right? So we can just label that here. And in terms of the width of the inlet, right? Since we already know that D is equal to 2 meters, right? So the W is equal to 0.5 meter, right? And then, for example, the length of the body, the LB here, right? LB You see that the ratio is 2, right? So, and also the dimension or the body diameter is 2 meters, right? It means that LB is equal to 4 meters. And the same thing, the LC, the ratio between LC and D is 2. It means that the LC is 4 meters too. So basically, for any type of the cyclone, so once we decide which type we're going to use, we just need to know one central parameter, which is the body diameter. Okay, so this is how we can find the dimensions for all the different parts of the cyclones. And then you may wonder, well, what does it mean by high efficiency or high throughput or conventional? Okay, so why don't people just choose high efficiency anywhere, right? Why can't we use high efficiency? Because our ultimate goal is to remove all of those particles. So the reason behind this design here is based on the cost, okay, or more specifically based on the pressure drop within the system. So if you think back on the mechanism for removing particles, right? If we come back to here, we're basically using the centrifugal force or the inertia of the system, right? So in order to improve the inertia, one thing we can do is to improve the velocity of the particle. So that is basically the inlet velocity going into the system. So which means that the higher the inlet velocity, the higher the efficiency, right? Because they were introduced inside with a higher velocity, and then it requires a larger centrifugal force. And if the drag force cannot support that, it means that the particles are going to get collected onto the wall, right? It's just going to collide with the wall here. So basically, it means that the higher the velocity, the higher the efficiency. And this is actually shown in this table here. We know that the inlet velocity, if you want to calculate that, that should be the flow rate divided by the cross-section area, right? And the cross-section area is H multiplied by W, right? So we know that it's just the flow rate divided by the area that the flow has to pass by. This is the inlet velocity, right? So in order to increase the inlet velocity, what should we do? We should decrease the height and W. So basically to make this inlet narrower, if we have a narrower inlet, then we're going to have a higher speed, right? And now if you just compare these values here, so you can see that for the high efficiency cyclones, we're going to have a smaller H and W compared to the high throughput ones, okay? For example, in terms of the height, right, you have 0.5 as the height of the inlet, right? But for the high throughput ones, you have 0.75, right? And then similarly for the width, you have a smaller width compared to the high throughput ones. So basically for the high efficiency cyclones, we're introducing, or what we're doing is that we just want to increase the inlet speed. But the thing is that in fluid dynamics, right, we know that the higher the speed, the higher the pressure drop, okay? So if the pressure drop increases, it means that the pump or the power has to increase, right? It means that it's going to take more electricity to drive the air through the system, and the cost is going to increase, okay? So that's why for the design of these cyclone systems, we will not always chase for this high efficiency. And as a matter of fact, if we want to achieve high efficiency for removing particles, we could use other PM removal devices. For example, the electrostatic precipitator or the backhouse filters, okay? But the cyclones are the best device to remove larger particles, for example, above 10 micron particles, right? So this is why people can have these design of the high efficiency. And similarly for the high throughput ones, so what that means is that we just want to send as much flow as possible, okay? So if you widen this, cross-section area here, you can allow more flow to go through, and then you're going to have a smaller pressure drop, okay? So the pressure drop decreases, and also the cost decreases. So each one of them are going to have some advantages and disadvantages. So that's why people combine these design parameters and get these conventional type or the more common type of these cyclones, which is somewhere in the middle, right? You see, in terms of the height, right? It's the same as the high efficiency ones. So both are 0.5, but in terms of the width, right? One is 0.2, the other is 0.25, the other is 0.375. So basically for the conventional one, it's just sitting between the high efficiency and high throughput ones. Okay, so this is how the design of the cyclone might affect the efficiency and eventually the power and the cost of the system. So now let's start to look at an example. Okay, so this is also the example on your textbook. All right, so it wants us to consider a conventional cyclone. So you see this keyword here, the conventional. So it means that we have to consider these two types of the designs, right? And generally, we're just going to use the first one. Okay, so when we mention high efficiency ones, we're going to use the first one. High throughput ones, the first ones too, right? So here we're going to use the design parameters of number 3, all right? So we want us to consider a conventional cyclone of classical proportions as described by Lapo, right? This is a Lapo's table here, all right? And then it has a body diameter of 1 meter, which means that B is equal to 1 meter. Okay, so this automatically can give us the dimensions for all different parts, right? Because you see everything, like height, the width, the length, right? They're all depending on the body diameter in the denominator, right? So theoretically, we can calculate all of the other dimensions. So it further gives us that the flow rate of the air is 150 meter cubed per second, right? Let me just write out these conditions, right? We have D equal to 1 meter, right? The Q is equal to 150 meter cubed per minute, right? The temperature is 350 Kelvin, and pressure is 1 atmosphere, right? So basically that's 1.01 multiplied by 10 to the 5th Pascal. And further, it contains particles with a density of 1,600 kilogram per meter cubed. So rho P is equal to 1,600. Okay. All right, so these are all the constants that's provided by the problem. And further, it tells us that we're not trying to solve the efficiency at a single size. We're trying to solve the efficiency for a size distribution. Okay, so it gives us a size distribution, which is showing the particle size range, and also the mass percent in this size range. For example, 0 to 2 microns, the mass percent is 1%, right? And 2 to 4 microns, that's 9% in terms of the mass, compared to the total mass, right? And 4 to 6, that's 10%, and so on and so forth, okay? So now it wants us to calculate the overall efficiency. So how do we solve this? So first, when we look at the overall efficiency or the overall collection or removal efficiency, if you think back, we actually give an equation to do this, right? So the efficiency was calculated by sigma mi, which is the total mass, right? And then we also take the sum of the efficiency at each specific size, right? Eta I multiplied by mi. This is because for different particles with different sizes, we're going to have different removal efficiencies. And then we have to consider what is being removed at each different size and then take the sum. So that's going to be the total removed amount, right? And then we'll take the ratio between that total amount over the total mass of the particles, right? So this is the equation we're gonna use. So you see that in terms of the mi here, we're already provided with all of these mass percentages, right? So basically, we just need to solve for what is the eta I, what is the efficiency at each size range, okay? So which equations are we going to use? We're going to use these ones, right? So basically, we need to first find out what is the efficiency at these specific sizes, right? But to do that, we need to first find out what is the cutoff size, right? What is the cutoff size for this cyclone system here? So any questions? If you have any questions, you can either unmute yourself or you can also just type in the chat, okay? So I just want you to basically follow what we're trying to do here, right? I hope I'm being clear in explaining these concepts. Okay, so if no questions, then let's just go ahead, okay? So you see that the goal is actually turned into trying to solve the efficiency at different size range, okay? So basically we need to first solve or first find out what is the cutoff size, right? So if we write out the meanings for each parameters again, right? So we know that the mu here is the dynamic viscosity, right? So the W here is the width of the inlet, right? The NE here is the number of effective turns, right? The VI, that's the inlet speed, right? And then rho P, that's the particle density. And rho G here, this is the gas density. Okay, so these are all the parameters that we have to use, right? So how do we solve all of these parameters? Okay, so first, in terms of mu here, I'm just going to write it out, let's say in here. Okay, so mu, that's the gas dynamic viscosity. So there are several ways. So I think eventually, if you see these similar problems in exam, I'm just going to provide you with the values, okay? But if you want to find out what they are, you can always refer to the appendix B2 of the textbook, okay? So you can find out what is the dynamic viscosity at any temperature and any pressure, okay? So you can find out in that appendix that at 350 Kelvin at 1 atmosphere, you're going to have the viscosity equal to 2.1 multiplied by 10 to the minus 5 Pascal second. Okay, so that's the viscosity. And then it's the W. Okay, so that's the dynamic that's the width of the inlet. Okay, so how do we solve that? So as we mentioned, we already defined that this is a conventional cyclone, right? We have that table that's provided by this. It's also called the LAPO table, right? So we're going to use this column here, and you can see that the ratio between the width of the inlet and the body diameter is equal to 0.25, right? And the problem told us that the diameter is equal to 1 meter, right? The body diameter is 1 meter here. So which means that W over D is 0.25. And we have W equal to 0.25 meters. And this is because D is equal to 1 meter. Let me just write it out. Right, so we can solve what is the width of the inlet. Okay, so now if you look at these terms, so 2 and pi, they're just constants, right? They have a value. And then it's the NE. So the NE is the number of effective turns And in last class, we mentioned that it's basically the ratio between the length of the cyclone body, right? It's a ratio between the length of the cyclone body and the height of the inlet, right? Because it's basically a parameter telling us how many turns these air can make within the cyclone. And if you see here, in terms of the movement of the air, right, it's going to move like ribbons. It's going to fall down and then go up. So in this scenario, you can estimate that NE is around 2, right? So it made around 2 turns and then get out. And to calculate this NE here, you have to find out what is the total length of the cyclone, because the longer the cyclone, the more turns it can make, right? And also you need to consider how high is this, what is the height of the inlet. And that's why when we solve it, we have the equation of NE equal to 1 over H, which is the height of the inlet. And then it's going to be LB plus 1 over 2 of LC. Okay, so the LB is the body of the cyclone, right? And then LC here is the basically for the conical part, right? Because the airflow cannot make complete turns anymore within this cyclone. Okay, so if I just draw out the approximate, let's say the approximate trajectory of the air, right? It's gonna move like this, right? So it's gonna make these turns and then go up. So that's why we have to consider the height of, have to consider the ratio of the heights. So I saw that Lane posed the question, so would there be a situation where NE is not a whole number? So yes. So NE is not necessarily a whole number. It's not necessarily an integer, okay? You can have half numbers. So basically that's what we call effective number, right? It can be even like, let's say 2.1, 2.2. It really depends on what are the exact dimension of the LB and LC, all right? Does that answer your question? Yeah, okay. So now we just need to find out what is the value for LB, LC, and H, okay? So again, we have to refer to this table, right? H over D for the conventional design, that's 0.5. Let me just write that out. H over D, that's 0.5. LB over D, that's what? That's 2, right? And also you have LC over D, that's also 2, right? So we can, I'm just going to circle these out. LB over D is equal to 2, and LC over D, that's also 2, right? And also we have what? We have D is equal to 1 meter, right? Which means that H is equal to 0.5 meter, LB is 2 meter, LC is 2 meters, right? So now we can plug in all of these dimensions into this equation here, right? So I'm just going to write this equation again. So NE is equal to 1 over 0.5. LB, that's 2. And 1 over LC, that's also 2. So that's basically 1 over 0.5 multiplied by 3, which is equal to 6. Okay, so the number of effective turns that the air make in the system, that's 6 turns, right? So this is NE. We got mu, we got W, we got NE, and then that's the VI, okay? So the VI, that's the inlet speed. Okay, so that should be calculated by Q divided by the cross-section area. Okay, so that's the flow rate divided by the area of the inlet, right? So that's H multiplied by W. Okay, so further, if you look at this problem here, it mentioned that the flow rate, right? The flow rate is 150 meter cubed per minute, right? So we mentioned that for this equation here, we have to use standard units. Okay, so the minute is not a standard unit. Okay, so we have to consider into convert it into seconds. So right, so 150 meter cubed per minute. So 1 minute is 60 seconds. Okay, so that's basically 150 meter cubed divided by 60 seconds. So that turns out to be 15 divided by 6, right? Meter cubed per second. And that's 5/2, which is 2.5 meter cubed per second. Okay. So you have the flow rate that's equal to 2.5 meter cubed per second. So we can start to plug it in, 2.5 meter cubed per second. And then we need to find out what is a H and what is a W. So we already actually looked into that, because here we already found out what is W, right? So what the W is 0.25. And here we also have the H, that's 0.5 meters, right? So that's going to be 0.25 meters multiplied by 0.5 meter. Okay, so you have meter squared in the denominator so that we can cancel the meter cubed in the numerator, right? So this thing turns out to be, so first you have 2.5, this is 0.25, right? You have a ratio of 10 here. That's 10/0.5, right? You're gonna have 20 meter per second. Okay, so this is the inlet speed. So we also got this solved. So eventually that's going to be the particle density. And luckily in this problem, it already tells us the particle density is 1600 kilogram per meter cubed. Okay, so this is also solved. And then it's the gas density. So we know that the gas density, especially for air, right? The gas density is much, much smaller than particle density, because one is in the range of like 1.4 kilogram per meter cubed, but the other is in the thousands, right? For example, here you have 1600 kilogram per meter cubed. So really, we don't need to consider this term, or we can just ignore this. And I have to say that for a lot of the calculations, you can just ignore the gas density. Okay, so we don't need to consider that in our calculation here. So in this case, I mean, I have to say, unless, all right, so unless the particles are very light, okay? So for example, when you're dealing with foam, right, foam particles, so they're going to have a very low density. But in general, let's say when we remove the particulate matter that's in the air, we just assume that the particle density is much, much larger than the gas density. Okay, so now we have all of these parameters. It's just a matter of plugging all of them in, right? So what do we have? We have dPc equal to the square root, right? This is to the power 1/2, that's square root, okay? So you have 9 multiplied by 2.1 multiplied by 10 to the negative 5. And then multiplied by W, that's 0.25. And then in the denominator, you have 2 multiplied by 3.14 multiplied by NE, that's 6. And then the VI, that's 20. And then you multiply 1600 minus 0. Okay, so we can just assume that the air density is close to 0 because that's too small. Okay, so this is the equation that we eventually got. So if you have a calculator by your side, you can start to type it in. And what I'll do is probably I'll just put it into a website. Okay, let me just share my entire screen. or just an Excel spreadsheet. So I saw that Mitch asked a question in this problem, is the gas density just the air? So what kind of examples would be other than air? I would say, I think for the scope of our class, we're just going to deal with air, okay? So maybe there can be scenarios where people may use the cyclones in water, right, to remove particles in water, but we're dealing with air pollution control, so we don't consider that. So I would say that you can feel very safe to just ignore the air density in this equation, all right? So now if we just plug in all of these values, right? So that's gonna be 9 multiplied by 2.1 multiplied by, or E minus 5. Right, then multiply 0.25 divided by 2, 3.14, 6, 20, 1600. Right, this whole thing to the power of 0.5. Okay, so this is what I get. I think you should be able to see my screen here. So I just put in the equation into an Excel spreadsheet. You can see that the number, or the diameter that I eventually get, is 6.25 multiplied by 10 to the negative 6 meters. All right. And so if you want, you can also copy this number down, maybe 6.26. Okay, this is 2599. All right. So now if we just go back to the equation. Okay, 6.26 multiplied by 10 to the negative 6. Oops. So what is this number in terms of micrometer? That's just going to be 6.26 micrometer, right? So that's what I said. In general, for a cyclone, in terms of its cutoff size, it's typically in the range of micrometers. So that's why it's very effective for removing particles larger than 10 microns, right? So because we know that at the DPC, the efficiency is 50%, right? So if it's above that size, it's going to be more efficient to remove those particles, right? So now we have the DPC, and so how do we finish up the rest of the things, right? So once we have the DPC, we just need to find out what is the efficiency for all the other different sizes. For all the different sizes, right? So we have eta j is equal to 1 over 1 plus DPC divided by eta pj squared, okay? So some of you may wonder what it means by this bar here. So bar here is the average size. So what does it mean by average size? So if you look at this table here, it's giving you a range of the particle size, okay? So 0 to 2, 2 to 4. So we're not going to solve the efficiency at any of the size in between. So instead, we're just going to look at the average size in this size range, okay? So we can first find out what is the DPJ bar. What is the average size in this range here? So let's say 0 to 2, the average size is just 1, right? 2 to 4, that's going to be 3. And then 4 to 6, that's 5, and 8, and 14, 24, 40, 75. So these are all the different sizes that we're interested in, okay? And then we need to find out what is the efficiency. So eta j is equal to 1 over 1 plus dpc divided by dpj squared. Okay, so it means that for this first size range here, that's going to be 1 over 1 plus 6.26 divided by 1 to the power of 2. Okay, so that turns out to be 0.02. Okay, basically this is 2%. All right, so we can try to plug in all the rest, right? 1 over 1 plus 6.26 divided by 3 to the power of 2. This turns out to be 0.18. So I'm just going to skip all of these equations, just write out the numbers, 0.39, 0.62, 0.83, 0.94, 0.98, 0.99. So basically we can find out what is the efficiency for any size within these different size ranges, right? So if we go back to this equation eventually, right? We find out what is the efficiency in that range. We know what is the mass fraction in that range. We can calculate the total mass concentrations, right? So we can just multiply these together, take the summation, and then divide by the total mass in this range, okay? So basically we can find out overall efficiency is going to be equal to eta I mi divided by the summation of mi, and you're going to get the final answer of 68.1%. Okay, so does that make sense? All right, so basically what we did is for this problem, in order to calculate the overall efficiency, we have to refer to this equation here, okay? So we actually trimmed down to the question of how to find all of these different efficiencies in different sizes, right? And we know that for the cyclone, in order to find the efficiency, we need to first find out what is the cutoff size. So that's why the question got converted into how to find all of these parameters in this equation. So we spent quite a lot of time to basically summarize or to identify all of these parameters. So once we got all of these parameters, we plug it in to find DPC. So we get a size that's in the range of 0 to 10 microns, right? That's a typical cutoff size, like the order of magnitude. And then we're going to use this DPC value to plug in to find what is the efficiency in different size range. So eventually we're going to find the overall efficiency. So I saw that Lane posted a question, is there a reason that in the example in the book, when they made the table, they found dpj over dpc instead of dpc over dpj? I think when we plug in the values, let's say when we eventually plug in these values, we're going to use the ratio between the dpc over dpj, right? So maybe in the table, it's just listing the ratio there, but eventually when they plug it in, they're going to reverse it and put it into the equation to find out the efficiency. Okay, so I also have the table in here, right? So you probably is talking about this table, right? So it's indeed using the dpj over dpc, but eventually when you calculate that, you have to reverse it and plug it in. Okay, so you don't necessarily need to list this column here. Okay, so as long as you can find out what is the particle size, you can directly plug it into the equation to find out the efficiency. All right. So does that answer your question? All right. Okay. So now, if I'm just interested in that, okay, so let's look at this problem again. So this problem is giving us this table here. So basically it's giving us the mass percent in different size range. So now if I ask you an old question, so how do we confirm that this size distribution follows log normal size distribution? Or the question is, does this size distribution follow a log normal size distribution? Okay, so how do we confirm that? So I think many of you probably already know that we need to use the semi-log plot, right? But the thing is that the semi-log plot is plotting the particle size against the cumulative mass fraction, but this is only giving us the mass percent in that size range. So how do we get the cumulative size, the cumulative mass fraction? We just need to add them together, right? For example, the cumulative mass fraction until 10 micrometer, that's just going to be the summation of all of these percentage from 0 to 10 micrometer, right? So let's see whether it follows the log normal size distribution. So if I just take the summation here, right? So from 0 to 2, let's say I'll just put MC, this is cumulative mass fraction in percentage, okay? So if it's up to 2 microns, we have 1%, right? If it's up to 4 microns, that's going to be 1 plus 9, that's 10%, okay? Because below 4, that's going to cover 2 to 4 and 0 to 2, right? So what about until 6? So we have to add these 3 together, right? So that turns out to be 1 plus 9 plus 10, that's 20%, okay? So we further for until 10, right? We have 50%, right? And then until 18, we have 80%, 94%, 99%, and 100%. Okay, so we have the cumulative mass fraction, and now it's just a matter of finding all the points and then see whether they connect onto a straight line, right? So how do we do that? We just list the values here again. Let me just copy all of these numbers. MC, that's 1, 10, 20, 50, 80, 94, 99, 100, okay? So then let's try to connect the dots. So first, in terms of the 2 microns, until 2 microns, we first find out what is size corresponding to 2 microns, and then the mass percentage is 1, so it's going to be here. All right, this is the first point. The second point is 4 microns, that's here, and then we find out 10%, that's here, right? And then 6, we need to find out 20%, which is here. And 10, that is 50%, which is here. Okay, it seems like it's following a straight line until now, right? 18 microns, that's 80%, right? 18 is somewhere here, right? 80% is here, right? And then 30 microns is 94. That's somewhere here, right? And then 50 microns, that's 99%. And for 100%, there's no way to plot that out, so we'll just forget about it. Okay, so is that a straight line? Well, it looks pretty straight. Okay. So basically what I'm trying to say is that when we try to analyze what is the overall efficiency of a cyclone, it doesn't really need this table here. Remember, for this problem, it's actually giving us this table for, I mean, just for for simplicity, to calculate the overall efficiency. But as a matter of fact, we doesn't really need this table. What we need is just a semi-log plot, right? For example, if a problem just give you a semi-log plot, let's say that we measure the size distribution to be following this this straight line here. Okay, this log normal size distribution. What is the overall efficiency for the cyclone? So what you can do is you can find out the mass percentage in each bin here, and then make a table that's similar to this one. And then find out what is the efficiency in different size range, right? Either J, and then find out the overall efficiency, right? So we don't necessarily need the problems to give us this table. It can only provide us with a straight line in the semi-log plot so that we can directly calculate the overall efficiency, right? Does that make sense? So I think in the homework problem, you're probably going to deal with a scenario that looks like this, right? So let's get to the end of the cyclones. So the cyclones, as we said, one disadvantage is that it has a pretty high pressure drop. Okay, so here this equation is giving you the pressure drop of the cyclone system. So it depends on the gas density, right? Although it's pretty small, but it still affects the pressure drop. The inlet velocity, the VI, remember we calculate that based on Q divided by H multiplied by W, right? And also depends on the HV here. So the HV is basically a pressure drop parameter, okay? So it's in the, it's expressed in the number of inlet velocity heads. And then we can further calculate this HV based on the other dimensions. Again, the height and the width of the inlet. The DE is the exit diameter, and the K is a constant. So in your homework problem, you're going to get provided with this K here. So you can calculate the HV and then further the delta P. Okay, so that's all for the concepts of the cyclones. So next class, we're going to deal with a new particle removal device. But before that, I think you have the homework where you can get some more practice on these systems. All right, so feel free to let me know if you have any questions. Okay, so I also provide, post this recording online in case you have any questions. All right, you all have a nice weekend.
You too.